Okay, so we might as well get started. Are there any questions from last time? Before I get going, okay. Note, I did re-upload the notes. I did find a typo in my equation for the Hugoniot. I had something similar with the enthalpies, but it is E2 minus E1 equals 1/2 P2 plus P1 times V1 minus V2. And then this should be the sensible energies. Okay, and so there is a typo there that I had in the notes. Is really the typo was in my master set of notes. But okay, so just pay attention to that and then fix that. So what we were talking about is we were doing a Rankine Hugoniot analysis for a reactive system to determine the possible types of combustion waves. If your system is pre-mixed, that means the fuel and oxidizer are already mixed, so your reactants just need to be heated up to a point where the chemical reaction can occur rapidly for the combustion wave to basically move forward. And so we went through the Rankine Hugoniot analysis, and the equations themselves turned out to be identical to that of what you get in what you used in gas dynamics if you guys took that class. And so they are actually one and the same. And so here in gas dynamics, and then we basically work with conservation of mass and momentum to produce these Rayleigh lines. And for these Rayleigh lines, we can show that the mass flux is that the mass flux that the slope of the Rayleigh line equals minus the mass flux squared by our combustion wave. And based on the fact that we don't want complex valued mass fluxes, which makes no physical sense, we could basically blot off these areas here of the PV diagram that are not admissible or that do not produce admissible solutions. And our Rayleigh lines are straight lines. And so they basically determine how fast the wave is going, assuming that because basically m dot double prime equals rho 1 u1. Okay, and basically rho 1 is known, and we don't really know, we don't know u1 yet. But we do know, but basically the steeper this line is, the faster the wave moves. And the shallower this line is, the slower it moves. And then we work with the energy equation, and then added a heating term. And basically what the heating term does was it took the traditional inert Hugoniot that you guys may have used in gas dynamics, and it basically shifts it up, or it shifts it up if the chemical reactions are exothermic, and it shifts it down if the chemical reactions are basically endothermic. And so this means that the Rayleigh line, there is a multiple variety of solutions to our system here. We have this branch up here. This is, and then this was called the detonation branch. And we have a lower branch. This here is called a deflagration branch. Okay, and so we briefly introduced those. And so, and we basically characterized the effect of exothermic, endothermic, and inert processes. And so we came up with this plot, and we drew all these lines here. And basically, so where is the solution? Well, we have our equation for the Rayleigh line, which is given by cap M here. So we have this equation for the Rayleigh line, and we have this correct equation for the Hugoniot. And basically the ES is determined by the equation of state. Okay, and so we have, and then we have this Hugoniot, and in conjunction with it, the equation of state. So essentially the solution to our system is where the Hugoniot and the Rayleigh line intersect. And if there are conditions where if there is a set of reacting conditions where they don't intersect, then there is no solution to our system. Okay, and so basically our solution is basically where the Rayleigh line and the Hugoniot curve intersects. Okay, and so basically for this here, I have drawn a Rayleigh line, and it's and just by my poor drawing skills here, but I've defined it to basically intersect this product Hugoniot 2 times. Okay, and so basically these for this case, the solution to our system for this particular Rayleigh line and this particular heating value is either this point or that point, and we'll characterize those in a bit later on. If you had for a flame, you could have a Rayleigh line go like this, and the solution to our system would be at this point here. Okay, or for an endothermic, you could have that as your solution point right there. But basically, it is the solution to our system is wherever the Rayleigh line and the product Hugoniot intersect. And remember that the product Hugoniot for the products is at equilibrium. So in other words, all of these Hugoniots for the products are assumed to be at their full chemical equilibrium composition. Okay, so any dissociation, things like that, if the temperature is very high, is already taken into account in these curves. Okay, and so as I said before, we have 2 completely different families of solutions. This branch up here is a detonation branch. And you can see here by basically just looking at the difference where a detonation could potentially cross a exothermic product Hugoniot. You can see that the pressure of a detonation goes up quite a bit, and the specific volume decreases just a little bit. And that's due, as I said on Wednesday, that's basically due to where the Rayleigh line intersects with the Hugoniot. It tends to be at a very steep portion of the Hugoniot, and that for an ideal gas, recall that for ideal gas, the Hugoniots, the Hugs, are hyperbolas. Okay, and then the origin of the hyperbolas is right there. Okay, and so that's why for a detonation, you are on the steep part of the product Hugoniot, and so you have a very steep Rayleigh line, and so at the solution point, you've changed the pressure massively, but you haven't changed the specific volume that much, and the specific volume decreases. So that means a detonation is compressing the material and increasing its density. And for this branch over here, down on the lower portion, I'll find a different color, purple. This here is the deflagration branch, and this would be what you classify as a flame. And so here, you notice the Rayleigh lines are basically have a very low slope. And so this means that a deflagration moves much more slowly than a detonation. And that will make sense from a physics standpoint after we start to examine the structure of both. And then also basically also a deflagration, for a deflagration, the Rayleigh line crosses the Hugoniot at the portion of the Hugoniot where it starts to become very, very flat. And so basically what this means is that for a deflagration, you have a massive increase in the specific volume and a very slight decrease, a very slight decrease in the pressure. Okay, so it's the exact opposite of a detonation. Okay, and so that basically characterizes, you know, on a very, very 5,000 foot elevation type level, that characterizes the big differences just based on nothing more than this diagram right here. That tells us what the differences are between a detonation and a deflagration, and we'll be examining some other properties of both. Okay, so are there any questions so far? Okay, so I've already talked about this. Okay, so now we're going to examine the inert case. Okay, so here we want to examine the case in more detail where Q is equal to 0. That means your product Hugoniot is just inert. And so that means it's actually the reactant Hugoniot. Okay, and basically here you've not changed the chemical composition. And so what happens here is that our equations are valid for inert as well as a reactive a system. So if it is inert, the sort of methodology that we discussed, where the solution is where the Hugoniot and the Rayleigh line intersect, which in this case is right here, that's still valid, even though the system is non-reactive. And so for an inert gas, this intersection point actually produces a shock wave. And so basically this intersection point here produces an inert shock wave. And so that is the same shock wave that you guys dealt with in gas dynamics and compressible flow. And so basically looking at things in terms of a shock Hugoniot, which is what this would be called, or shock Hugoniot. Is essentially how this would be looked at by a physicist. They tend to think in terms of Hugoniots, or by somebody working in basically blast wave theory. They tend to be worried about the Hugoniot of the reactants, although they may plot it in terms of different variables, but it's still a Hugoniot. Okay, and so basically we can learn from this is that for the shock wave, our system starts at state 1 and it doesn't follow to state 2 along either the Rayleigh line or the Hugoniot. And what happens then is that the system, because basically the only valid solution points are where the Rayleigh line and the Hugoniot curve meet, right? And well, they only meet here and they only meet here. And so what this means then is that our solution jumps from state 1 and it jumps to state 2. And so that means that our shock wave is a true discontinuity. If you had a process that followed the curve, it would not be a shock wave. It would not be a true discontinuity. But in this case, we have a true discontinuity because it basically, our system teleports from state 1 to state 2. Okay. And then, so are there any questions with that? So this is the same shock wave that you guys learned about in gas dynamics or comp flow, if you guys did that. Okay, and so this is just another way of deriving those relations. Okay, and then note for our analysis, based on gas dynamics, if Q is equal to 0, actually you can show if Q is less than or equal to 0, basically it's endothermic or there's no heating, you can show that this region here violates the second law. Okay, because basically we have derived our Rankine Hugonios assuming that there was a jump, a sort of a jump between state 1 and state 2. And basically, so this would imply that basically this curve here would imply that you have an expansion shock with strict Rankine Hugonio. What you would need to do to fix this, to extend our theory for an inert case with Q equal to 0 in this branch over here, is you would need to would need to replace this curve over here. You would need to replace it with an isentropic expansion curve. Okay, and then with the isentropic expansion, you can now basically get solutions that are basically in this region. But for isentropic expansions, our solution can actually follow this line here. Okay, and so the physics is a bit different. So just be aware of the fact that if you're dealing with an inert shock wave, basically this region here is also forbidden by the second law. Okay, so so for shock physics, the only relevant branch is this upper branch right here. Okay, so are there any questions with this? Okay, now we have now we're going to consider the case where we have chemical heating due to chemical reactions. And so we have a instead of our product Hugonio being attached to the origin, it's going to be pushed up slightly. And so here we see when we draw our Rayleigh line, for a given Rayleigh line, there can be up to 2 possible solutions. Okay, we can have this Rayleigh line here that has 2 solutions. We can have this orange Rayleigh line here that has 0 solutions. And we can have this special blue Rayleigh line that has exactly 1 solution. And then the same goes for both the upper and the lower branch here. Okay, and so for both the detonation branch up here and the deflagration branch down here, we can have basically 2 solutions, 1 solution, or no solutions, basically just depending on the chosen Rayleigh line and the Hugonio curve. Okay, and so now we're going to go and basically analyze these cases here in a bit more detail. So are there any questions here? Okay. So first, let's examine a special limiting case. And so a special limiting case are these blue Rayleigh line cases here where they just barely touch, where they're just actually, where they just touch the Hugonio curve at exactly 1 point. And note, even for the most realist of gases or equations of state, I am not aware of any product Hugonios that do weird things like this, and you would have a case where your Rayleigh line could cross your product Hugonio a whole bunch of times just based on weird curvatures of the product Hugonio. I think you can show thermodynamically that these regions here of the product Hugonio would not likely be physical. Okay, so you don't need to worry about the case where the Rayleigh line and the product Hugonio can intersect a whole bunch of times, just based on the equation of state. And even if there were, there would be some special rules for basically doing those crossings. But we are not going to get into that stuff in this class. Okay. So, but now let's examine what the Rayleigh line would look, or what the solutions would look like, basically using this tangent point as a sort of separating between, basically as a way to separate the Hugoniot curve into 5 distinct regions. Okay, and so first we will define the tangent point of the limiting Rayleigh line to the Hugoniot curve. We're going to call those the Chapman-Jouguet points. And those are tangent. Okay, and so you can see that we have two Chapman-Jouguet points, or 2 CJ points, is what they are commonly called. And so we have two CJ points. We have one for the upper branch, and then another one for the lower branch. And so the one for the upper branch is called a Chapman-Jouguet detonation, or a CJ detonation, and the one for the lower branch is called the Chapman-Jouguet deflagration. Okay, and then if we use these 2 points here as basically separating 5 different regions here, we have a region here above point U, which is the upper CJ point, or a CJ detonation point. So we have a point where the pressure is higher than that. That's called region 1. We have region 2 here. I'll draw that a little bit better. We have region 2, which is on the valid region of the detonation branch, but it is below below the CJ detonation point. We have a region 5 here, which, as was noted on Wednesday, that even though the Hugoniot curve mathematically can basically cross into this region, it is forbidden. And so basically region 5 here is a forbidden portion of the Hugoniot. We have region 3 here, which is the point where the specific volume of a Chapman-Jouguet flame, or a CJ flame, the specific volume is less than of the products is less than, or is less than that of the is right here. So it is less than that of, or where the pressure, or yeah, we're basically to the left of the of this lower CJ point, and we have region 4, which is to the right of this lower CJ point. Okay, and so there are different properties to all of these different different regions, and this would not be V2, this would be P1. Okay, so are there any questions with this? So basically, we just looked at the limiting cases of basically when the Rayleigh line is tangent to the Hugoniot, and basically separated the potential solution regions into basically 5 different groups. And then these points here are called the Chapman-Jouguet, a Chapman-Jouguet detonation, or a Chapman-Jouguet deflagration. Okay, depending on which one we are looking at. Okay, are there any questions? Okay. And so, as I said before, the 2 tangent points are called the upper and lower Chapman-Jouguet, or CJ points. There are 5 sections on the Hugoniot, and I really wish these iPads could show a bit more on the screen at the same time, but I can't. So region 1, which was above U, is called a strong or overdriven detonation. Region 2, which was below you on the upper Hugoniot, or the detonation branch. That's called a weak detonation, or sometimes it's called an underdriven detonation. Then region 3, and this is these are on the deflagration branch. Okay, we have region 3, which is on the left side of you here. This is called a weak deflagration. And we have region 4, which is to the right of you. This is called a strong deflagration. Okay, and so there are different properties of them. And also there is region 5, which is forbidden, as I said before. And all of these 4 different regions have different sort of characteristics of the combustion wave. Okay, and one of the most prominent of them is determined by Jouguet's rule, which you can actually prove mathematically just based on the physics. I did it one time for a different class, and it's a 2-hour proof. But anyways, what Jouguet's rule states is that the burn state, which is state 2, is supersonic, and that's with respect to the wave, if the slope of the Rayleigh line is greater than the slope or is less than the slope of the is less than the slope of the Hugoniot. No, that's right. Is basically greater than the slope of the Hugoniot. And the opposite is true if the slope of the Hugoniot is less than the slope of the Rayleigh line. And so what does this mean? This means that if we look at, if we have a Rayleigh line that is basically crossing through basically this point here, is that the Rayleigh line has to start at the origin and then go up. And so that means at basically this potential solution point here, the slope of the Rayleigh line is less than that of the Hugoniot, and we can conclude based on Jouguet's rule that for these cases here, that the products of the combustion wave are subsonic with respect to the combustion wave. And in this region here, we have the exact same opposite, where we have that the Rayleigh line is steeper than the Hugoniot, and this means that the products are supersonic with respect to the wave. And for those of you who've done Rayleigh flow in gas dynamics, that should be raising a huge red flag to you, because we have a constant area duct. It's well insulated. So essentially here, we have a combustion wave here, but gas dynamically, it's just a compressible flow with basically heat added to it, which is basically what we are analyzing right here. And you know from gas dynamics that you cannot, through heating alone, you cannot take a flow that is subsonic and basically accelerate it to a supersonic condition. There's essentially no way of doing that. And so, so this should already be raising some red flags about region 2 right here. Okay, and that's just based on Jouguet's rule and just consequences of gas dynamics. Okay, and so basically Jouguet's rule just states that we can start to examine the properties of these solutions and find which ones are physically real, and find which of those 4 regions is physically realizable. Okay, and so now what about those special tangent points? Is that first of all, we could argue that just based on this curvature here, they are on the boundary of the region where the product flow is subsonic up here and supersonic down here. And they have to meet smoothly, and also based directly on Jouguet's rule, the slope of the Rayleigh line and the slope of the Hugoniot are the same because they're tangent points. And if that's true, then that means that the products exiting a CJ combustion wave are actually they are actually sonic with respect to the wave. Okay, and so this means that basically U2 at both of the Chapman-Jouguet points is equal to the sound speed, C2. Okay, and recall that for an ideal gas, that's given by gamma RT, or more generally square root of partial P partial rho at constant taken on an isentrope. Okay, and so the products are sonic, and that has really some special that has a sort of special consequences for detonations. And after we discuss the detonation structure, the fact that the products are sonic, that means basically it's really hard to quench a detonation after they get started. It's extremely difficult because they are basically isolated. Because any information from behind the detonation wave cannot basically mess with the structure of the detonation. That it has no way to enter it. And so because of the sonic condition of a detonation or Chapman-Jouguet detonation, it is really hard to stop a detonation after it gets started. Okay, and basically we will discuss that point more as we move on. Okay, and now one thing is that the one thing about the special Chapman-Jouguet points is that the sonic the so-called sonic condition provides another relationship, another constraint that allows us to uniquely find the CJ points. Because if you think about it, here is that essentially, if we're trying to find the solution to our system and say it's right here, we only know what the state of the reactance is. We cannot, and we have to specify how fast the flow is sort of coming in. But because we know nothing about state 2, with the exception that it is at full chemical equilibrium. That's the only thing that we know about state 2. And so, but we don't know rho 2, we don't know U2, we don't know P2, we don't know the temperature at state 2, etc. And so basically all of those can be determined by the equation of state and the Hugoniot relations, but we still can't uniquely we still cannot uniquely determine the speed of the wave. Is that some other information is going to have to come in to determine how fast that wave is going, and for flames and for detonations, that those are completely different physics. What determines how non-Chapman-Jouguet flames and detonations propagate. But the CJ points are different. Is that here we have a condition where the products are moving at the speed of sound, and so we can actually uniquely determine these 2 points based only on thermodynamics, and that's it, only on thermodynamics. Okay, and so basically adding this criterion on, and basically adding that to your equation set, in addition to the Rankine Hugoniot conditions, allows us to uniquely find these CJ points. Okay, and it's really important to note that the CJ points are determined only by thermodynamic considerations. How fast the chemical reactions occur is not important at all to determining the Chapman-Jouguet detonation velocity or the Chapman-Jouguet flame speed. Okay, and that's really important. I see in papers every now and again people making mistakes with that. And so the CJ points are determined by the state of the reactants, that's P1, V1, T1, etc. They're determined by the equation of state, and they're determined by the properties of the chemical equilibrium of the products. And this is all in chemical thermodynamics. Okay. The CJ points are not determined by chemical kinetics or molecular transport. Okay. Okay, and so the CJ point or CJ detonation depends only on the thermodynamics of your system. That's it. It depends on nothing else. And how fast the chemical reactions occur does not matter, and molecular transport does not matter for determining those 2 points. Again, within reason, if your chemical reaction was so slow, it took 30,000, it took 30,000 centuries to complete, you would not have any combustion wave, of course. But any sort of reasonably fast chemical reaction mechanism will produce the same Chapman-Jouguet detonation, regardless of which chemical reaction mechanism you use. Okay, and so that is very important because every now and again, there will be a paper that comes across my desk to review, and it will be entitled something along the lines of the impact of chemical reaction mechanism on the Chapman-Jouguet detonation velocity. And the answer to that question is it doesn't. And the fact that they showed sometimes that it does, that means that their code is broken. Okay, and so that's a very important point that sometimes folks make. Is that the CJ points are uniquely determined only by thermodynamics. Chemical kinetics plays no role. Now, if we're off of the CJ point, then basically this rule it basically no longer holds. Then it starts to depend on chemical reactions. Then it starts to depend for a deflagration. It starts to depend on molecular transport. Okay, so are there any questions with this point?
So the whole point of the reaction, considering the CJ point, is just the CJ point is not affected by it, but the path that it takes may be affected by it, and that's really, or not, doesn't change it, but it would just be a different path depending on the reaction.
So and the reason I keep saying CJ detonation is that we will argue later on that a Chapman-Jouguet detonation is the only 1D planar steady detonation that is stable. Either the other ones are unstable with the CJ point as an attractor point, or they are unphysical. It is one or the other. So as Vincent just said, where the chemical kinetics plays a role is determining the structure of the wave itself. So right now we have a black box approach. We are just looking at what's going in. There's some sort of magical combustion wave inside of it, and we're just looking at what's going out. But if you wanted to determine the structure of that combustion wave, then you need to consider molecular transport if it's a flame. Don't need to consider it if it's a detonation. And for both, you need to consider chemical kinetics. And we will start discussing how to compute the structure of a detonation on Monday, probably. Okay, but that's a very good point. Okay, any other questions?
And then just to make sure on the Jouguet rule up there, between the slopes of the Hugoniot and the Rayleigh line, I think it's down a little bit. That the second part of that statement there, should that be Hugoniot greater than?
Yes.
Okay, just wanted to make sure I was reasoning with that right.
Okay, any other questions? Okay, so now we'll just examine the detonation portion of the branch. The deflagration portion of the branch would be way down here. I'm not going to plot them. So basically we have our inert Hugoniot, or our reactant Hugoniot, our product Hugoniot here, and we have three different Rayleigh lines. Okay, we have the green one, which produces no solution. We have the special CJ1, which produces a CJ detonation. And we have a generic blue one that produces strong and that can produce strong and weak detonations. Okay, so what can we tell based on Jouguet's rule and this Hugoniot curve? Okay, first of all, if we start from a very shallow Rayleigh line and swing it up, we will eventually hit we will eventually hit the sort of CJ detonation point. Or if we start from a steep one and reduce the slope, we will eventually hit the CJ point. So what this means is that the slope of the Rayleigh line that produces the CJ detonation is the smallest slope, or is the Rayleigh line with the smallest slope that produces a solution to our system. So in other words, that basically the sort of mass flux, which again is related to the slope of the Rayleigh line, that the basically mass flux of reactants that is being processed by the detonation wave at the Chapman-Jouguet point is the minimum mass flux that can be processed by a detonation. Or stated differently, assuming that the reactant density is constant, which it is, that the fact that this Rayleigh line here that produces a detonation solution at the Chapman-Jouguet point is the lowest slope means that the CJ detonation is the slowest possible detonation. Okay, and so basically the U1 is minimum at the CJ condition. Okay, or the CJ detonation velocity, DCJ, is minimum is the minimum detonation velocity for a given state of the reactants. Okay, and so basically the slowest possible detonation is the Chapman-Jouguet detonation. All other detonations are faster. Okay, and the products of a strong detonation based on Jouguet's rule they are subsonic. So that means that we have our reactants here, and they're being processed by the detonation into products. And then based on Jouguet's rule, we can state that the velocity of the products is basically less than the sound speed, and then that's just based on Jouguet's rule, as I've written here and then argued before. So why is this important? Well, think of your gas dynamics. Is that a detonation has some structure, it has some width to it. Like right now, we are ignoring that structure. But say if the products are subsonic, and say we put a little speaker in the product state, and we play a song to the detonation, what will happen is, because the products are subsonic, that means our acoustic waves that are produced by the speaker can propagate to and interact with the detonation. Okay, and so that means that you would expect that any acoustic wave that is produced behind the detonation wave can propagate to and interact with the detonation. And so then what happens is that strong detonations are not stable, and then they are weakened by acoustic waves. They are weakened by acoustic waves that basically enter into the detonation wave structure, which then reduce the rate of chemical reaction and then basically slow it down. And it slows down to the point to where the products are sonic, and to where these acoustic waves produced by the speaker can basically no longer make it inside inside of the detonation wave itself. And we will discuss more about that when we discuss the structure of the, when we start discussing the structure of the detonation wave on Monday. Okay, so any questions with that? Okay, and then,
Professor,
yeah,
so Jouget's rule applies even if it's not a curve with a Rayleigh line that has a CJ point.
yes,
Okay.
yeah, it's just, it's basically any crossing point of the product Hugoniot, or of the Hugoniot in general, and a Rayleigh line.
Okay. Okay.
Yeah, it is not just the CJ point. Okay, and then the other point is that the products of a weak detonation are supersonic with respect to Jouget's rule. And this is usually unphysical unless there are very special cases that can produce weak detonations, because you know that just because you know that you can't spontaneously accelerate by heat and heat alone a flow to supersonic supersonic conditions, that it's just simply not possible unless you have very special cases. And experimentally, you can produce a weak detonation. And we will, again, we need you need to start looking at the structure equations to analyze how to do that. And we will discuss that starting on Monday. Okay, and then also you can also prove, I'm not going to prove it, but you can prove that all detonations are supersonic with respect to the wave. So basically, the flow going into a detonation is always supersonic. So that means if I were to basically, if I were to let this detonation move forward, it would travel at a supersonic velocity. For a gas, that'd be about Mach, would be about Mach 5. It would be about a Mach 5 wave for a gas that it'd be propagating into. Okay, and so all detonations are supersonic, and then that can also be proven. I'm not going to prove that for this class. That is also another lengthy proof. Okay, and so typical properties of detonations. Basically, the speed of and I should say CJ, because that's where they tend to live, is that the velocity of the detonation, dCJ, is on the order of 1 to about 2.5 kilometers per second for gases. Again, extremely fast. And for solids, it's about between 5 and 10 kilometers per second for high explosives. And they are always supersonic waves. The CJ pressure over P1 increases, is the CJ pressure bumps the pressure up by about a factor of 10 to 50 for gases. So that's why if you have a hydrogen air explosion, it produces so much damage, because the detonation wave just suddenly bumped up the pressure by about a factor of, say, 10 to 20. Okay, and for high explosives, the CJ pressure over the initial pressure is about 10 to the 5. Yes, if you do the math on that, the CJ pressure is between 10 to 40 gigapascals, and that's why explosives produce so much damage. Is that 10 to 40 GPa is well above the yield limit of any solid material, meaning that if you are above the yield limit of any solid material, it can start to flow like a liquid, and that's part of why high explosives produce so much damage. Is that basically nothing can really contain them unless you have a really huge block of material. And so detonations produce very strong compression waves, very, very strong. Okay, but there isn't that much change in the density or specific volume. Is that for a gas, the density of at the Chapman-Jouget point will be about 1.5 to 3 times that of the reactants. And for solids, it is only 1.4 times higher, and that's a very close sort of well-used rule of thumb, that if you know nothing else about your explosive, that the CJ density will be about 40% higher than that of the reactants. Okay. And also, I'm not going to prove it here. This would be a nice little homework problem. Is that you can show that for a moving detonation, that is if the reactant state is stationary, you can prove that the velocity of the products follow the detonation wave. Okay, and so basically, that the products move with basically move with the detonation. Although even though they follow the detonation wave, they move nowhere near as fast. Okay, and so are there any questions with this? Okay, and then we will finish up by just discussing bulk properties of the deflagration branch on Monday, and then we will start getting into the structure of the detonation wave itself. Are there any questions?